So in this video, I want to do two things. First thing is to go over this example with spherical harmonics and give me an opportunity to sum up some things that we learned about the spherical harmonics. And then the second thing is to go over the radial solutions to the time-independent Schrodinger equation for hydrogen, and the hydrogen potential. So then we could understand the orbitals of hydrogen fully. So we're not talking about spin. We'll save that for the next lecture in class, but we'll understand the three quantum numbers n, l, m sub l, and how they relate to the mathematical form of orbitals. Okay, so we left off last class on this example. So these are the answers for all of the spherical harmonics. So you can start to tell a little bit better. So I want to remind you of what the normalization condition is. So you'll notice, like, if you square this, it's not quite equal to 1, right? What are we integrating over? So remember that the normalization condition of 1 is equal to the integral over all angles, right down the limits of the second y, and so pi squared. Transformation variables from to spherical, get this leftover sign of the polar angle. So we're integrating this thing squared sine theta d theta d phi, where theta, the polar angle, goes from 0 to pi, and the vehicle angle goes from 0 to 2 pi. So this is the normalization condition. If you plug in, the easiest one to play with is 0, 0, this first spherical harmonic. If you plug that in, you get 1 over 4 pi. You can take that out of the integral. You can show that the integral, so integral sine theta d theta from 0 to pi is 2. And then over the vehicle angle, you get 2 pi. So that total integral is 4 pi, and then divide by 4 pi is 1. This satisfies that normalization condition. You can check this for any one of these. And actually, part A is to check that this is true for y1 minus 1, which would be this one, but doing the bottom sign. So -1 would mean that in the e to the I pi, it's e to the minus I pi. So I guess the most important thing to notice here is that in any spherical harmonic, so that there's of course the normalization factor. Sine learns they're all y, so we can kind of ignore that, right? That deals with the issue that we're going to need at all in this class. So normalization factor, then there's a part that depends on theta, and a part that depends on phi. And the part of it that depends on phi is really easy. It's e to the I times n sub l times phi. That part's really easy to guess. Like if you just do the value of that value, you don't define dependence there. The theta dependence, I mean, these are hard to guess. These are polynomials called Legendre polynomials. But for the polynomial, you plug in cosine theta. I mean, it's a little weird. You could be given a spherical harmonic. You didn't know what it is. I mean, I guess I kind of expect that you know that this one is a constant. Other than that, you could. Okay, so we have an idea of how to do part A. For part B, we already know what answer to get. Okay, so there's two ways that you can do part B. There's the easy way and there's the easy way, which is just we already know that since these are eigenfunctions, eigenstates, these two words independently, eigenstates of the total angular momentum operator. So for all of these are special functions where this is equal to square root of L times L plus 1. So since it's the square, where it's this thing squared times the function. So with this, we have a function where L is equal to 1 and m sub L is equal to -1. We know that if we act the total angular momentum operator on this function, we should get this eigenvalue back. So we should get a constant times the function back again. That constant should be 1 times, in parentheses, 1 plus 1. So that's 2 h bar squared. So we guess, so we should get, should get eigenvalue 2h bar squared. And for the other one, the L sub z operator, L sub z operator, and I'll show you the mathematical formula of these in my previous slide. This is m sub L h bar. So for this problem, this should be, if we plug in m sub L is -1, looks like we should get minus h bar for the eigenvalue. So these operators are right here. The L squared operator, so we take all of this, I put on the YL m sub L, and simplify as much as we can and see if we get a constant and this one's a lot easier to check, right? So to give you a feeling for what the solution is all about, so to check that it's normalized, you want to actually square this and integrate sine theta, d theta, d phi. So we're just plugging in this one right here. So the 1 minus 1, right? So this one with the minus sign. So we have a sine theta, so the constant kind of comes along for the ride and we take it out right here. So we have sine squared, and then the sine theta, the denominator of that all combines to give you a sine cubed. It's the math one you problem. That's it's 2. It's sine cubed, sine squared. It's pretty great in terms of cosine. If we use substitution equals that is because d was minus sine. Integrate it over u, then turn it back into theta and plug in the limits of integration. And after all that work, you just get the number 1. But it's nice and easy. Maybe just plug in the down here. A little bit more. So it's just you can expect it to take derivative, but you haven't had to actually so then for B and C are to check the y1 minus 1. And we didn't write this out, but this is always theta comma math. The function was showing this. It's to check that this function is an eigenstate of the total angular momentum squared operator and the z component of the angular momentum. So it's just taking derivatives and simplifying. So it's probably looks hard to read, which is, this is how we go when we look at your work. Change derivatives and you get the your work. It's not too fun, but eventually you can convince yourself. You can all take derivatives. You can convince yourself that you get 2h bar squared. It requires a little bit of you have to play with this to show that that stuff just winds up being a constant. Right? That's not obvious at all. But you have sine squared on the denominator for 2 of the terms. If we make that third term, the -1, the first term on the left there, if we make that term sine squared minus sine squared over sine squared, then you can combine everything and then use the trig identity, sine squared plus cosine squared is 1. That helps you figure out that you can combine these in this way. Or in other words, you can replace the cosine squared with 1 minus sine squared, and the 1 combined with the -1 minus sine squareds combine and then cancel with the sine squared on the bottom. So that's probably the hardest part of this, is to recognize that you can simplify the term of these coordinates. So y1 minus 1 is eigenstate of L squared is eigenvalue plus 2h bar squared, which that would be best that we should get that very simple formula. So that's good. And the other one, the minus h bar derivative. So this kind of shows why e to the m sub L I phi, that part just comes down, and that's the part that's left over as the eigenvalue. So this one's a lot easier to do. And you get minus h bar. So that's a good example. So I want to talk about this part today here in this video. And say spin for then we'll take so what we did, we took time independent Schrodinger equation in spherical coordinates. And the only thing we were assuming there was that the potential function was a function only of radius, not of theta or phi. So in doing that, we could separate out the theta phi dependence and the r dependence completely. And the last lecture was all about exploring the solutions to the theta and phi. Those solutions are spherical harmonics. So, but we're still, to really know the whole wave function, we have to know the radial. So the radial part of that time independent Schrodinger equation is this. So we separate it out. We call the constant that's separating the two. So it's a simple constant. We call it like L plus 1 for this. We write it in the way that this comes from the constant separating to the other stuff just comes from the weirdness, like why these two terms right here. This comes from the weirdness of the Laplacian operator. It has several terms in it, so we act on the wave function area. The first derivative with respect to r and a second derivative with respect to so the only thing remaining, so this is true for any central force, potential force or potential energy that depends on the environment. So the only thing left to do is to plug this in for the potential energy. This is what makes it hydrogen, or hydrogen-like, if you put the dependence in. So all we need to do is plug that in there and see what the solutions are. So then, would you solve this is not very important. It's like a week of talking about math. And even that, it's not very satisfying. It's just like a series of guess and check almost. But what you can do is you can take the solutions and verify that they're solutions, right? You can take any one of these are the answers, and plug them in just to verify that they're solutions. So, so radial wave functions are labeled by two integers, n and l. So n is called the principal quantum number. So this is like, a lot of times we're talking about orbitals like 2s, 3p, that sort of thing. That first number is the value of n. That's the most important thing. And the n value tells you the energy of the state. And actually, you only need to know the n value to know the energy of the state. So the energy of a wave function only depends on the n value. It doesn't depend on L or M. So all those different spherical harmonics told you nothing about the energy of the state. No magnetic field. We'll talk about after you add in the magnetic field. With no magnetic field, there's the only one n value. The L value is the same constant that appears in the spherical harmonic. So this lowercase l offset is the same value as the L y. L is the shape. For L equals 0, it's called S. This is called the P. We normally put the letter right next to the number. It's 1s, it's 2s, it's 2p, this is 3, that's 3p, and L equals 2 is for every one of those combinations of n, there's a certain function, the radial. It has its own separate normalization condition. Remember, 1 had to be equal to the integral from r1 to 0 to infinity of the radial function n L. So we're integrating, so we take the square of any of these functions, so this thing squared. And remember, we have an r squared left over from that Jacobian transformation. So it's integral of r squared, capital R squared, times lower r squared, the lowercase r. So one interesting thing about the ground state, just for 1 second. So the ground state, and then just regular hydrogen, you plug in z equals 1. A naught is called the Bohr radius. This is the same Bohr radius as we saw before. So it's like half a angstrom, 45 times 10 to the minus 10. The constant times e to the minus r over a naught. So that the wave function is exponentially decaying as a function of distance. The wave function is, and remember that for this one, the radial, the angular register comma is constant. This one. This is 1 over 2 square root of 5. So this side's going. For any s, yeah, for any s or both those. So actually, the total wave function for ground state of hydrogen is you multiply these two pieces. Just a 1 over 2 square pi times this thing would be the ground state of hydrogen. So the ground state of hydrogen, the wave function is an exponentially decaying function of distance from the origin. So psi is largest at the origin, and it gets lower and lower. However, and this is a weird thing to think about for a while. Because of this r squared integral, you can ask the question, what's the most likely distance that the electron is away from hydrogen? So you might say that because psi is biggest at the origin, you might say it's at the origin. It's most likely to be at the origin. Ask what radius is it most likely to be. But if you plug in r equals 0 in this interval right here, that kind of attenuates, it diminishes the likelihood of being near the origin. So you have kind of two competing effects. You have this r squared that increases as you go farther away, but then you have the exponential decay of the wave function. So actually, the most likely radius for hydrogen, if you ask what's the most, if you measured where the electron is, and you asked what's the most likely outcome for what the distance is that electron is away from hydrogen, you actually don't get 0. You get the Bohr radius. Actually, so that has to do with maximizing the possibility density as a function of r. So it'd be r squared times the lowercase r. This thing right here. You want to see when that's a maximum, the integrand of that integral. Wherever that's the maximum, that's the most probable value to look for. So a little bit of, so if you haven't seen chemistry, this is lower here, but if you haven't, this is the wave functions for hydrogen are completely specified by 3 quantum numbers. So once you know these 3, you know the spatial wave function. You know psi of r theta phi. So the wave functions of hydrogen, we need psi of r theta phi. So we'll know exactly what the wave function looks like in all places. Those 3 numbers. So the first most important number of these 3 is n. So choose that one first, and that will be the energy of the state. And this n you should think of as very similar. And the reason we call it n, which is similar to the Bohr radius n. Sorry, the Bohr. And notice how this formula right here, the energy of the state, this is actually the same exact formula as what Bohr. Theory that predicts something incorrect. So it's a totally different approach for what's going on in the hydrogen. We actually get the same exact answer for the energy. It's kind of amazing that as simple as the Bohr model was, so this E sub m is still minus 13.6 eV. times 1 over n squared, or if you had another number of these squared. So n is the most important number. From 1 to 1 yeah. Once you choose n, there are only certain values of L that are possible. Just in terms of solving this differential equation, just in terms of categorizing all of the solutions have to have this property. This is where this comes from. So any value, but then once you know n, L can only be 0 up to n minus 1. So n can have any value, and once you choose that, you're limited in values of L. And then once you choose L, then you're limited in the value that n sub L could have. It can only go from minus L up to L. So there's an infinite number of possible functions. There's an infinite number of the structure of how these quantum numbers are related. There are some limitations, there are some rules to get from. Really, we just care about the first few values. These are the most important when it comes to putting electrons in a hydrogen. So, 2 more slides. So, you can pause the video and try this one. How many wavefunctions, how many different size? So, there are different ways of phrasing this. How many different size, how many different combinations N, L, and M sub L exist? Maybe the wavefunctions might exist with N less than or equal to 2. Then pause the video and try this one. Okay, so n less than or equal to 2, so we can't have n equals 0, so we can have n equals 1 or n equals 2. So for n equals 1, we have to choose L equals 0. We have to choose n sub L equals 0. So there's the state 1, 0, 0, following this ordering. Because that's one of the things. So for n equals 2, we have 2 possible values for L. We have L equals 0, and we have L equals 1. Now, if L equals 0, then M sub L has to be 0. But if L equals 1, M sub L can be 3 things. So then M sub L equals -1, 0. So we have stage 2, 0, 0. But they have 3, so then we have 2, 1, -1. We have 2, 1, 0. And we have 2, 1. So counting all of the different states here that we've listed on the right-hand column here, looks like we have 5 possibilities. Right? So as a general formula here, the number of wave functions for every n value is n squared. So for each n there are n squared orbitals for wave functions. So here we have n equals 1 or n equals 2. For n equals 1, there's 1 orbital. For n equals 2, there's 4 orbitals. 2 squared is 4. We add up the 1 and the 4. So you can write down the formula for what every possible wave function is. So the n, L, and here instead of n sub L, they just call it n. It's a complicated looking formula, right? We just wrote down what all of these were here for some lower values. But it turns out there's an actual formula that polynomials just keep growing in terms of their power. But they're called Leary polynomials. So AGU so polynomials follow a certain form, but basically this is proportional to the radial part of the wave function, proportional to. And then right here you have the spherical harmonic. Just going to squeeze in at the end because that's all of the beta and phi dependence. So these are the pictures. These are the orbital that you saw in chemistry. This is the map behind where these things come from. So it looks like they didn't draw out 1s. This would just be a single 2s figure right here. So the only these things. 3s. The 2s orbital has what's called a radial node. This right here is called radial node. Position. This is a general thing that the higher the energy levels go, the more nodes you have. So actually has 0 nodes. 2, that equals 2 orbitals. 2s or 2p have 1 node. 2s orbital has a radial node. And then the 2p orbital has an angular node. So you notice that right here, again, I guess for the picture drawn, it would be like again, theta is pi/2. On that whole plane is where you have wave function equal to 0. So this is called an angular node. An angular node is a plane where there's 0 probability of conflict. So as the n increases, the more total nodes you have. So radial plus angular nodes. The total number of nodes is n minus 1. So for 3s, the 3s orbital, it looks like we have 2 angular nodes. For the 3p orbital, we have 1 angular node and 1 radial node. So as a result of this increasing number of nodes, there's like an increasing kind of chaos that you see going on in these orbitals that you put down in these pictures. They're cool pictures, and you know that this understanding that this is what they look like helps inform why molecules form the way that they do. So you might say, well, what evidence do we have? That it's really hard to image, a single atom, a single atom of clicking like this. They don't stay excited for very long, so we can't just like set up a 3p orbital and have it sit on that really probe it. The kind of tricks that you can do. Really, the main evidence that we know supporting this, that these pictures, they really tell us how they're going to bond to other atoms. Understanding the look like this really good. Streak to take off. Throughout the whole microgrid, they're predicting what molecules could and cannot form based on the shapes of the world. So that's really the power of knowing mathematically what it's going to. Okay, I think that's enough for this video, and then we're going to continue this on with CMOS effect, which is related to a magnetic field. Magnetic fields and spin